Okay, so at this point, we made this particular choice, okay? What is the antiderivative of e to the x? Isn't it just e to the x? Everybody? Now, we're done with the integration. Here's where we will put in the plus c. Okay? I'm claiming that the antiderivative of this is this. I'm pretty sure it is. Okay? You guys okay with pretty sure it is? I'm almost 99% half sure that I did it right. Can we have certainty?
Yeah. Oh, sorry, my voice is
How do we have
dying.
certainty?
E to the x integrated is just e to the x plus
Right.
c.
I'm
and
pretty sure this is the right answer. Are you guys okay with I'm pretty sure it's the right answer, or can you be certain it's the right answer? How can I know that I did it right?
Can we just do the derivative?
Take the derivative of your answer. That's how you always check your integration. If we were in baby algebra and I said, here's a polynomial, I want you to factor it, and then you wrote it as the product of factors. If I said, how do you know you're right? You said, well, let me just multiply them back out again. I am doing an integration. I think my integral is correct. We'll just differentiate it. If I get back the original integrand, it has to be correct. So let's do that. It is always wise to check your answer because it's not all that hard. Oops, x e to the x. So I'm actually using product rule. So I'm going to get first times derivative of the second plus second times derivative of the first. Is that the answer? So hold on a second. Plus hold the phone a moment. Minus integral of e du. Oh, I'm sorry. I'm looking at the wrong. I'm sorry. I want to differentiate this guy. Sorry. I was looking at the wrong one. We have one more term. Sorry. Like that's not all the way there. There we go. First times derivative of second plus the second times the derivative of the first, and then minus the derivative of this guy, which is just e to the x. And I got back the original integrand. You don't have to do a lot of problems before you can get pretty confident that you're doing them correctly. It is always wise to check. Sometimes the check can be really long, though, because the problem itself might be really long. So integration by parts. The key that I recognize, I have the integral of a product. Now I want to correctly identify the u and the dv. Now, this is not an absolute rule. This is one of these, the vast majority of the time, but not 100% of the time. When you have polynomial-ish and transcendental functions, e to the x, trig, inverse trig, those are called transcendental functions. When I have something that's polynomial in nature and transcendental, I usually want to pick that guy as my u because each derivative then gets smaller, okay? And so what happened? The derivative, I had no more x's after one derivative, and that made it really simple. When you have a function like e to the x where you can do the derivative or the antiderivative, sine and cosine, you all know the derivative and the antiderivative, then sometimes you have choices. If you have a function and you only know the derivative, then that kind of limits your choices. If you only know the derivative, then that has to be your u. So let's do another one. We're going to do a lot of problems today. You know, write the overall formula on the top. I started recording just a little late. So again, the idea is I have something of this form, then my answer is uv minus the integral of v du. Now, I do have printed notes also, and I have some practice problems on Canvas of this so that you get a little bit of extra work. So what if, let's do one with sine and cosine now. We'll do a similar problem. I have x cosine of, actually, let's see, x cosine of 2x. Make it a little more interesting. I know both the derivative and the antiderivative of cosine. So technically, cosine could be my u or it could be my dv. I know the derivative and the antiderivative of x. But if I choose x for my u, then du will be constant dx, and I will have less stuff. So that's the best choice I could make here. So I will let u equal x and the dv equal cos 2x dx. Then the du is 1 dx. You don't have to write the 1. I do to remind myself that I actually did take the derivative. And the v will be, what will v be? Anybody? We should know that. Antiderivative of cos 2x. Nobody wants to take a chance.
Sine 2x divided by 2.
Well, it definitely have a sine 2x. So the question is it
Divided
Time?
by 2.
Well, how about times a half? Yeah. Coefficients, you never want to write in a denominator, just makes everything kind of messy. I only have 2 possibilities. It's either going to be a 2 or a 1/2. The derivative would have a 2, the antiderivative would have the reciprocal. So now what do we got? We got uv. So how about 1/2 x sine 2x minus the integral of v du. So minus a half sine 2x dx. Now I just have a sine function. I just have a sine function, so therefore I don't have to do parts. I can integrate that one directly. So I'm pretty sure my final answer is going to include this term. Okay, plus or minus. The easiest way to think about this is what function, when I take its derivative, will be minus sine? What function looks like negative sine when I differentiate? Probably something involving cosine, agree? All right, I'm going to go out and put the cosine. Is it plus or minus? You only have 2 choices here, plus or minus.
Plus.
So if I differentiate positive cosine, I get negative sine. That's good. And now my coefficient. Because when I differentiate, I get the extra 2. So this coefficient has to be what? Is it a half times a half or a half times 2? A little bit of rust here. Yeah, you shouldn't have to think too hard here. It's an absolute, you always do the same in integration when you have a constant multiple of your x. It's always the same for all functions that exist. You never have to think twice. Am I going to get an extra half or an extra 2?
A half.
It's going to be half. Differentiating gives me a 2, so integrating gives me a half. So that's going to be a 4th. And now I'll go ahead and put the plus c. Now, this answer looks kind of icky, and the check is going to be a little messy, but we can all do that. That's a piece of cake. But the beautiful thing is, if I said what function when I take its derivative looks like this simple product, it's this big mess. Nobody saw that in their head. But that's the thing. The only way you can get a product of functions after taking a derivative is to differentiate more than one thing and then hope things combine and cancel. That's what integration by parts does. It gets us back to that piece. All right, let's continue. We're not, like I said,
Why did it switch to a plus again?
well, what's the derivative of positive cosine? Negative sine. It didn't switch, you integrated.
Yeah. Okay, yeah. I see.
When it's sines and cosines, we all know that the plus or minus, we all have issues with sines and cosines because it's plus in one direction, it's always minus in the other. So what I like to do is, rather than tell everybody what's the antiderivative, and I teach Calc 1, I say the same thing. Don't think what's the antiderivative of this. Say what function when I differentiate it gives me this. Sometimes it's easier to think in those terms. When I differentiate cosine, I get negative sine. So it's got to be cosine. Well, technically that makes cosine my antiderivative. Because the danger is we may accidentally take the derivative when we're trying to integrate. And sines and cosines are notorious for that kind of stuff. All right, let's keep going. I got exactly one plethora of examples to do. All right, now we got x squared times e to the about 4x. Ooh, this just got really, really icky. X squared. Now, once again, both functions, I know both the integration and the antiderivative. I know the integrals and the derivatives in both of these. But because one of them is polynomial and the other is not, it's probably safer to choose the x squared as my u. Okay. I could try it the other way, but all that would do is make my integral grow bigger and uglier. So then du is 2x dx. V is what? What's V? 4 or a fourth? You guys are thinking again. All antiderivatives have the same rule. Infinitely many functions that all have the same rule. There's no exception. When you integrate, you take the reciprocal of the coefficient, absolute, all problems that exist, no exception. So if you're having to think what goes there, that's really, really bad, by the way, because that should have been day one practically of integration. It's a 1/4. Because when I differentiate, I get the 4. If you're thinking about what goes there, then it means there's one of the most important rules of integration has somehow left you. That's not one you should have to think about. That you didn't think about putting the 2 in front. Same thing. Some things should be automatic. The reciprocal of the coefficient is one of them. And then I can always, let's see, is that true? When I differentiate, I'm going to get a times 4. Okay, good. I'm back to there. So now what do we got? We got uv. And you notice I'm writing it in an order that's easier to read. I put the coefficient in front, minus the integral of v du. I have a half and I have a fourth. By the way, would there be any harm in putting the half in front, 2 times the fourth? That might not be a bad idea because then I'm not worried about it when I integrate. It's kind of out of the way. And then this would be x e to the 4x dx. Okay, great. Oh, but wait a minute. I don't know how to do that one. So did we do the wrong thing? I used integration by parts and I still have something I don't know how to do that one. We started with an x squared though, now it's just an x. Anybody got an idea? Completely radical notion here, anybody?
You substitute again.
Do it again, yeah. Do integration by parts a second time. Oh, okay. We do it a second time. Now, here's the thing. When I do it a second time, and this is not uncommon, when I have x to a power, I might have to do integration by parts that many times, by the way. But your choice, what should I do with my choice? Now, don't write the next thing. I'm going to do something altogether terrible, okay? I'm going to show you what happens when you make a poor choice at this point. And yes, you might shrivel up like the Indiana Jones character. I'm going to reverse my choice. I'm going to make u be e to the 4x, and I'm going to make dv be x dx. Then du is 1/4 e to the 4x, and v is 1/2 x squared. I'm using the black to show you it's a different problem. I'm going to erase it eventually. So watch what happens to this guy. So my answer is 1/4 x squared e to the 4x minus 1/2. Now I'm going to do this. So uv 1/2 x squared e to the 4x minus the integral of v du. If I did that right, so that'd be minus 1/8. Hold on, minus the integral of. Oh, I'm sorry. Oh, my bad. That should be a 4. Ah, look at that. That looked weird to me. So uv minus, oh, here we go. There we go. And then v du should be 2x squared e to the 4x. All right. Now let's go ahead and distribute. And you're going to notice something really cool happen right about now. Okay. Minus 1/4 x squared e to the 4x plus the integral of x squared e to the 4x. Great. Oh, look at these guys. They cancel. Awesome. So I've got the integral of x squared e to the 4x equals the integral of x squared e to the 4x. I just filled up a page of writing and I now have the original integral equal to itself. What happened to all my good work? Anybody? What happened to all this beautiful work in blue?
You reversed it.
When I reversed the choices, I just undid everything. By the way, this is an absolute. This will always occur. And a great many problems, you will have to do integration by parts twice. That happens often. If you reverse your choices of the u and the v's, you will always end up with the original question and no work will have taken place because you will literally undo every step. I have to show you this for you to see it. I don't ever want you to do this. Never. That's why I didn't even want you to write it down. So when my choice of u was the polynomial and the dv was the exponential, then in round 2, it has to be the same thing or this problem isn't going to work. Okay, that's a money back guarantee. That's why I didn't want you to write it down because, you know, very frustrating. But again, we're avoiding our heads shriveling up like the guy in the Indiana Jones movie. That's, you know, that's very below average. Okay, so here, like before, we're going to now choose u to be x. dv, once again, is e to the 4x dx. Then my du is 1 dx, and my v is 1/4 e to the 4x. So now, let's go back. All right. uv minus the integral of v du. So that's just minus 1/4 e to the 4x dx. That one's easy. I know I can do that one. Okay. Anybody? What's this going to give me? That's going to give me minus what e to the 4x? What goes here? We should not be struggling with that. I'll give you a hint. Even if I didn't know the antiderivative of e to the x, I know what goes there. I can have a function I can't integrate, and I know what goes there. What goes here? Everybody.
1/4.
So the coefficient's the same?
Oh, 1/16.
How about 1/16? Yeah, 4th times a 4th. Now, this is still within the bracket. Why am I doing that? Because I still have to also distribute. Oh, so I got to multiply these guys. So don't be in a hurry, because when we're in a hurry, we might lose things. I'll drop down a little bit. And I'm going to put the plus c. Now, that is the answer. That is a perfectly acceptable answer. You may not love all the fractions. It doesn't really matter. Now, is this the best representation of the answer? There's, by the way, this is not an absolute. Is this the best representation? Well, it's the question is, what am I going to use this answer for? I'm in a physics class. I'm doing things that involve measurements. Now, most of you are probably familiar with something like this. Maybe you're in a physics class and you've got the ramp and you have the little go-kart going down the ramp, right? Little Pinewood Derby like in Cub Scouts. And every 1/10 of a second, you're measuring how far it went and you're going to eventually chart the distance and the speed and all that. You know, you're doing a physics experiment. And that means I have to evaluate something maybe 20 or 30 or 40 times. That's not unusual, particularly in physics. If I had to evaluate this function many times, there's a lot of places I got to plug in an x. But all 3 of these terms have an e to the x, or e to the 4x. Might it be efficient to factor out the e to the 4x? Do you think that might be a good idea? Anybody? If I've got to use this to do calculations later, might it be wise to factor out the e to the 4x?
Yes.
Yeah. Is it required? No. You do not factor an antiderivative. You always, without exception, you factor a derivative, period. There is no exception. You always factor a derivative because the only relevant information is where does the derivative equal 0. And you can't do that unless it's in a factored form. But you never set an antiderivative equal to 0. There is no application. Therefore, you never have to factor an antiderivative. I have 3 terms all with an e to the 4x in them. It just makes sense to factor it because I think it would be easier to work with. If this is the answer, then this is the answer. But can I improve upon this? Perhaps. So if I factor out the e to the 4x, it definitely would make calculator work easy. Now, what about the coefficients? I have 3 fractional coefficients, and we all know that that could be a little bit of a headache to plug into a calculator. Is there a GCF of these 3? The greatest common factor of 1/4, 1/8, and 1/32? Which would be the greatest common factor? There is definitely one.
Four.
Well, these are all fractions, so it's probably another fraction.
32.
1/32. Let's factor out 1/32 e to the 4x. This is what I would do. And what would that leave me with? Well, clearly an x squared. I'd have to multiply this by 8 to get to here. So how about 8x squared? How about the next one? Minus, well, what would I have to multiply this by to get to here? I think 4. So how about 4x? And I just factored out the entire thing, so plus 1. Now look at that answer. This is absolutely correct. This is about 1.6 bazillion times easier to work with and much faster on a calculator. And I only have 1 fraction. I only have 1 e. So if I had to actually do multiple calculations, this would be light speed compared to this. Do I have to do this? No. But if I was in a physics class where I was using this, yeah, I would definitely want to do that. Remember, I mentioned this last day, when you're doing a problem in calculus, we're getting a calculus answer and we're thrilled and overjoyed that we were able to do the problem. But understand, in real life, you're not going to have a job where somebody hands you a sheet of integrals or a sheet of math questions and says, finish all these, solve them, and then I'm going to give you your paycheck at the end of the day. Like, yes, I'm going to solve a bunch of math problems and then get paid. Nope, no one's ever actually going to ask you to solve a math problem. They're going to give you a situation. And you have to figure out how to change the situation into a math problem. And then the math problem might have many, many, many steps. And the integration is only one of the steps. In fact, it's often maybe the first step of the problem. And now I got to use it to answer a whole bunch of other questions. So it's never about what is the right answer. It's about what's the most useful form of that answer. That is the answer. And if you told me that, I'm thrilled that you got it right. But if I've got to use this now to answer more questions of a higher nature, I might want to re-express that in a form that's simpler to manipulate. I just want you to be aware there might be a form that's simpler to manipulate. And there are a lot of problems out there, by the way, where I can have an answer be absolutely correct and it looks very different from somebody else's answer who's also correct. And we're going to address that today too. Multiple representations of the same answer that do not look the same, but actually are the same. You know, think of things like trig identities and such along the way. All right. Now let's try another one of these bad boys. How about I've got x to the 12th power times the natural log of x dx. Oh my goose. So I'm going to have to integrate this guy. I have to do this 12 times? Maybe. Okay, let's start the process. Most of us would say, let's let u be x to the 12th, and then dv is log x dx. So then du is 12x to the 11th, and v is what's the antiderivative of log x? Does anybody know the antiderivative of log x? You don't know the antiderivative of log x? Good, because we don't have an antiderivative of log x. We know the derivative of log x. We don't know the antiderivative. Oh, so that means I can't do the problem? No, that means that has to be my u. See, e to the x, sine x, cos x, x to a power. We know both the derivative and the antiderivative of those guys, but there's not a whole lot of functions that we know the derivative and the antiderivative. For the natural log, we only know the derivative. So it can't be the dv, it is forced to be the u. And that's what makes your decision. I said the vast majority, but not all the time. I said the vast majority of the time when you have an x to a power and a transcendental function, the majority of the time you pick x to a power as your u because you knew the antiderivative of the other guy, e to the x, sine x, cos x. But because we don't know the antiderivative of the natural log, That dictates my choice, but it also makes the problem, believe it or not, much simpler. If I say now let u equal log x and dv equal x to the 12th dx, what's du? Anybody? I think we know this one. Anybody? What's the derivative of the log x?
Oh, 1 over x.
Yeah, so this will be 1 over x dx, and then the antiderivative of x to the 12th. X to the what power? Antiderivative.
13.
13, and then 1/13. Oops, sorry. And that's, sorry, I didn't leave myself any room there. Try that again. V equals 1/13. Now, you're going to like this because it turns out this is one of the shorter ones, not one of the longer ones. So my answer is UV. So how about 1/13 x to the 13th log x minus the integral of v du. 1 over x times x to the 13th. Isn't that just x to the 12th? Oh my goose. I can do that one. That's easy. All right, you might need your calculator. What's the antiderivative of 1/13 x to the 12th? Well, it's definitely x to the what in my answer? Yeah, use your calculator.
13th.
And then what's my coefficient?
Is it 169?
Yeah, 13 times 13 is 169. So 1 over 169. Wow, that wasn't that terrible. Now, once again, because I have the same term showing up more than once, you may choose to factor it. You don't have to. You may choose to because you might find it convenient. Okay. So that wasn't too terrible. Now, I want to remind everybody of some of the ones we know and the ones we might struggle with. Anything polynomial-ish in general is typically easy to work with. The transcendental ones, those are the ones that require a little bit of practice. You might have to, go back and look at your formula sheets. Now, there's a vocab term here. I've used it multiple times already. Transcendental. And everyone, oh yeah. No, I didn't go. I have no idea what he means when he says that. In fact, your calculus book might say something like this. Let me grab one. See, what does that say? Single variable calculus, early transcendentals. Great, even my book has that word on it, and I still don't know what it means. Transcendentals are kind of important. There's two types of functions. There's only two. There's algebraic and there's transcendental. And here's one of these great definitions. The definition of a transcendental function, non-algebraic. You see, together they make the whole. They're complements of each other. So if I don't know what one is, then I don't know what the other. Yeah, it's one of those, you know them both or you don't know either one. A transcendental function, an example of a transcendental would be a trig function, an inverse trig function, exponential, a log, a hyperbolic. An algebraic function would be anything involving a polynomial to a power, a root of a polynomial, a quotient of polynomials. So when you think algebraic, think polynomial-ish in general, and then transcendental is kind of like everything else. So all the ones that had special rules, you know the derivatives of all the trig functions, the log functions, the exponential functions, the hyperbolic functions, the inverse trig, you know those derivatives. You know how to differentiate any polynomial and any polynomial raised to a power. But you treated those separate. Those didn't require a separate set of rules. You just had to remember how to differentiate the exponent part. So integration by parts usually always occurs with one of your functions, if not both, are transcendental functions. So they don't have simple integral rules. One of them doesn't have to be an x to a power, although it often is, because they show up that way. So let's do probably one of the ickier ones. And sometimes icky is cool. We like icky, I think. All right. I want to integrate e to the x sine x dx. I have two transcendental functions, and I know the derivative of both. I know the antiderivative of both. Therefore, either one could be the u. It would not take any longer. It does not matter what my choice is. I'm going to get the same answer in the end, no matter what I choose. Okay, so let's just go ahead and pick e to the x to be the u, since it's first. And then dv will be the sine x dx. And my du is e to the x dx, and my v is what? Positive or negative cosine? Anybody?
Positive?
I'm integrating. The derivative would be positive, so
Oh,
negative cosine. Yeah, that one always gets us, doesn't it? So I got uv, so negative e to the x cos x minus the integral of v du, but there was already a minus, so I can go ahead and put plus e to the x cos x dx. Everybody cool? This is flawless so far. All right. Well, I think it's obvious I have to do it again. Okay. But I'm definitely going to pick the u. I learned my lesson, by the way. Again, I don't want my head to shrivel up. I'm definitely going to pick the u to be the e to the x. And then the dv will be cos x. Then the u will be e to the x dx. And what will v be this time? Again, it's a question, is it going to be positive or is it going to be negative?
Positive sine of x.
Positive sine x, good. So now we've got negative e to the x cos x plus uv minus the integral of v du. All right. Houston, I think there's a problem, but I'm not sure. Did we just get the same problem back again like we did before? Or is this not exactly the same? It's close, but it's not exactly. Do I have exactly this on the right side? Do I have exactly the same thing on the right side?
no.
No,
It's
that negative sign, if that were a positive sign, then, you know, they kind of cancel. That would be bad. No, it's a negative sign. So what do? I'm going to add this to both sides. Why would I do such a thing? Because now on the left side, I have 2 times the integral of e to the x sine x dx equals negative e to the x cos x plus e to the x sine x. Right, catch that? Because that was a minus, I'm going to throw it over to the other side, therefore doubling the left side. My goal was to find that integral. So how about it's half, and now I'll put plus c. This is one of the more difficult ones for most people, but this is pretty common. When you have a product of transcendental functions, you're probably going to have to do parts twice. But in the case of sines, cosines, and e's, they kind of cycle around because the derivative of e and the antiderivative of e stay e forever. The derivatives and antiderivatives of sines and cosines just keep producing each other forever and ever. So in this case here, it worked because this was the opposite sign. So when I threw it over, boom. You notice we never actually integrated this, but we did get the answer on the other side. Would it be correct to factor out a 1/2 e to the x? Sure. But again, like I said before, you don't have to. Just be aware that that's an option. Sometimes when you're checking your answer, you know, through a source, maybe technology, or you're checking your answer in the back of the book, the answer might look different, but it's the same answer. Always be mindful of that. Okay, so this one's kind of tricky. Now I'm going to do a little bit of background because I've used this before, and a lot of folks somehow this escapes them. Probably the majority, if not all of you, when you do a problem, you feel good about the problem, and then you check your answer through another source. Now, if I'm doing an integration, I don't check my answer by integrating it again. When I ask algebra students, how do you check your answer? And they say, well, I just do the problem again more slowly and more carefully. And you realize that all human beings will make exactly the same mistakes, just slower and more carefully. That's like saying, I wrote an English paper. I'm going to check it by writing the paper again. I'm going to misspell all the same words because that's how I thought they were spelled. No, you don't ever check something by doing it again, because if you got a different result, well, I believe that's the definition of crazy. No, you check it through another means. You check factorization by multiplying it out again. You check integration by differentiating, the obvious. But sometimes, like this one here, I don't know about you, but I don't really feel like differentiating that. That's kind of icky. So here's what I do when I'm checking a big gnarly one. I will do big gnarly integrals all the time, and I will get an answer. And I need to know, is my answer correct? So rather than integrate it again, I just differentiate my answer. But I will now use technology to differentiate my answer because I am interested in getting the correct antiderivative. I already know how to differentiate, but I also know this differentiation is going to take a little while. So here's where I will go to Wolfram or something and just say derivative of this. And it's going to give me back my original integrand, or it is not. If I don't get back my original integrand, then I know I made a mistake and I go and I find it and fixed it. If I get back my original integrand, then I know I did it right. I never integrate using Wolfram, just so you know. The reason is I can always get an answer faster and more accurate than Wolfram. I can get an answer that's one term and Wolfram will give me 4. And anybody's used Wolfram, 7 of your answers that you get are going to be complex. Wolfram will give you double-digit answers to a simple question, most of them being complex and all of them being way, way busier. Not incorrect, just way, and you go, wait, I could have condensed that into one simple quotient. So I don't use it for integration. I use it to check through differentiation because it's just easier. Okay, so if I want to check this answer, I need to know that I'm right. Is it possible I messed up a plus or minus somewhere? Well, of course, that was something we potentially did along the way. You want to be right, you want to know you're right. And you also want to know, is my representation accurate? Now, here's a problem that I do in Calc 1. And probably at least half of you, if not most of you, were in my Calc 1. So you may remember doing this problem. Okay. Some of you guys remember the row your boat problem? Yeah, this is that one. So here's what we're going to do. All the people on this side, you're the row your boat people. All of the people on this side, you're the gently down the stream people. Okay. So here's how it works. I'm going to give one integral. This is a Calc 1, not a Calc 2 problem. Now, when I look at that integral, couldn't I choose either one of those as my u? Because the derivative of sine involves cosine, the derivative of cosine involves sine. Yeah. So the row your boat people, you're going to choose u to be sine x. The gently down the stream people who have kind of a superiority complex anyway, you're going to choose your u to be the cosine of x. And you're both absolutely correct in your choices. So what we want to do is do this problem down to the bitter end, because I want to illustrate a very, very simple point, but one of the most important points that we're going to have over the next 3 weeks. And that is, you're going to do problems perfectly, and you're going to check your answer, and it won't look anything like your answer. So therefore, you will automatically assume you're incorrect when you are absolutely correct. And I'm going to show you how you get around that issue, because it's going to be a common one. So in this case here, my du would be cos x dx. Over here, my du would be negative sine x dx. So this problem over here simply became u du. But over here, oh, I need that extra negative, don't I? So I go negative, negative, and so now I have negative u du. If my u is cosine, then my du needs to be a negative sine. Okay. Row, you both people, you got 1/2 u squared plus, let's call it C1. Gently down the stream people, you got negative 1/2 u squared. We'll call it C2. Because I'm doing the same problem twice, it's unlikely my arbitrary constants are going to be exactly the same. So we'll call them 2 different things. Now I substitute back. My u was sine, so I got 1/2 sine squared x plus C1. Great. Row your people, you guys are feeling really good right now. Yeah, all you gently down the stream folk, you're looking very suspicious at the row your boat people. There's your answer, there's their answer. Who's right? Or either one of you right? Ooh, in fact, not only did you get different functions, by the way, can the square of sine or cosine be negative? Is it, or is the square of sine or cosine going to be positive or zero? What do you think? The square. The square of sine and cosine. Can that be negative?
No.
No. So clearly that's a positive answer. Clearly that's a negative answer. So are they both wrong? Is one of them wrong? Are they both? These people did it this way and they're feeling pretty good. And they're looking with great suspicion of these guys. These guys did it this way, and they're not even going to invite those guys to their next party because they clearly don't know their mathematics. I maintain both answers are absolutely flawless. Positive sine squared, negative cos squared. Seriously, one's positive, one's negative. Don't we know that cos squared x plus sine squared x equals 1? So therefore, doesn't sine squared x equal 1 minus cos squared x? Do you agree? So isn't this 1/2 times 1 minus cos squared x plus c1? Which would be 1/2 minus 1/2 cos squared x plus c1. But c1 is an arbitrary constant. So 1/2 plus c1 would be a different arbitrary constant. And voila, they are exactly the same answer. They were both done absolutely perfectly. And everybody in this class, if you haven't had this experience, it's because you didn't do enough problems. Everybody in here has done the problem flawlessly, and you checked, and a different version of the answer was the one you saw in the textbook, or when you did it checking using technology, you got a different version. So therefore, you assumed you were wrong. Now, whenever I see that something else was different, I assume I'm right, and it's just a different representation. And then I try to see, can I get from one to the other using maybe a trig identity or just something? And usually I can. Now, occasionally, yes, there is an error involved, but often it's the case that you were flawless, but the other person just took a different route. Both of these answers are absolutely correct, and one is not considered better than the other. So my point being, if there are options in a setup of a problem, there may be alternate versions of the answer that are truly equal, and you can get from one to the other using an appropriate substitution, such as this. Okay, so those of you who are in Calc 1 with me, you remember doing this and going, oh yeah. Do not assume you're wrong if your answer doesn't match. See if there's a way of getting from your answer to the other. So I used factoring earlier, saying a lot of times it's efficient to factor out an answer. But sometimes when you check your answer, the factored version may be the one that's in the solution. And yours didn't look like that, and say, can I make mine look like that? It would be wise rather than assuming you're wrong. Okay, let's try another one. We got a lot of these in us right now. How about I would like to do the integral of tan x dx. Okay. But you're going, Mr. Brown, you said we don't know the antiderivative of that. So let's find it. Well, my u is log x, I know that, but I need a second function. Well, you have one. Don't you guys see the second function? Oh, come on, you guys can't see the second function? It's right here. What's my second function?
1.
1. Can I do that? Oh, yes, I can do that. In fact, I just made this problem really easy. How did I make it easy? Because if your u is log x, then your dv is 1 dx. Then what is your du?
1 over x.
1 over x dx, and then what is your v? You don't like
X.
this one. Just x. So according to integration by parts, my answer should be uv minus the integral of v du. Oh, wait a minute. What's x times 1 over x? That's just 1. What's the integral of 1 dx?
X.
So are you telling me the antiderivative of log x is x log x minus x? I don't know. Let's check it out. All right. first times derivative of the second, plus second times derivative of first, minus the derivative of x. Well, that's 1, and I have 1 minus 1, and oh my gosh. Yep. Turns out there's a lot of functions that you know the derivative of, but you do not know the antiderivative of. Think of all your inverse traits. You know the derivative of inverse tan. You know the derivative of inverse sine, inverse secant. You know the derivatives of more complicated functions without knowing the antiderivative. So if I was asking you the antiderivative of a complicated thing that you didn't know, you can always try integration by parts, make the one you don't know your u, and make the number 1 your du. Isn't that cool? We just got an antiderivative for a function that doesn't have an antiderivative. Well, there is no single function that when differentiated produced log x, but there's a combination of things that when differentiated produced log x. All right, let's do this again. Let's try it with, how about one of my personal favorites? How about inverse tan? Inverse tan is a really important function, and we all know the derivative, because the derivative is not that bad. But I don't want the derivative, I want the antiderivative. Oh man, you had to ask the antiderivative? Well, can we do the same thing? Can I think of this as times 1? Let's all try that, okay? In fact, I'm going to give you guys a little bit of a head start. Start this problem for me. Because I don't know the antiderivative of inverse tan, it has to be u. Okay. What's the derivative of inverse tan x?
1 over 1 plus x squared.
Good. 1 over 1 plus x squared dx. And then over here, I'm going to get b equals x. Okay. So we've got that this is uv. So x inverse tan x minus the integral of v du. Since that's a quotient, I'll just go and put the x on top. Well, now that's interesting because look at my new antiderivative. It's a quotient of polynomials. It's a rational function. And one of the things we're going to learn in this course, we don't know this yet, over the next couple of weeks, we're going to learn that you can integrate every rational function. But we haven't learned all rational functions yet. But this is a calc 1. You see, think u sum. If my u is 1 plus x squared, then what's my du?
2x.
Can I do that? Is that legal? I just put a 2 in front of the x and put a 1/2 in front of the integral. Can I do that? Oh, you know what? I realize, hold on, let me do this. I just looked up and I saw the glare. It doesn't always show up to me. I'll put it down here. Minus the integral of, there we go. So if my u is 1 plus x squared, then my du is 2x. So not only is that legal, can I give the antiderivative of that without doing any work? What's the integral of 1 over u? Isn't it log u? So my answer is x inverse tan x minus 1/2 log 1 plus x squared. Oh my gosh. Now, normally when we integrate something and we get a log, we put absolute value. My argument is 1 plus x squared. Tell me something about 1 plus x squared. Now, this is a calc 1 problem, the second part. 1 plus x squared is always 1 plus x squared.
Positive?
Always positive. Do I need the absolute value if it's always positive? No.
No.
It would not be incorrect. It just wouldn't be necessary. 1 minus x squared can be negative. 1 plus x squared is always positive. So the answer to my question, that's crazy. This is one thing that's really nuts. You integrated an inverse tan and you got a logarithm in your answer? Yeah, and we're going to see over the next couple weeks is a really, really strange brotherhood between logs and inverse tans. Logs and inverse tans show up together very often in answers. They don't show up in all answers. But what happens is if one shows up, the other one usually does too. They're kind of a package deal. It's crazy. But we're going to see it. It happens quite often. Now, the check for this, a little bit messy, but we could all do this. So we integrated a transcendental function that we didn't know the antiderivative to, but we knew the derivative, and it turns out that is enough. Okay, that is actually enough to do this. Let's see. We're good so far. Let's keep going. Now, I'm going to if you go to the dictionary and you look up evil, I always have fun with that because sometimes evil is more fun. We all know that. Yesterday in my Calc 3, we discussed evil three-dimensional surfaces, and we found a really cool one, probably the most important one we deal with in Calc 3. Well, when you look up evil in the dictionary, there's a whole bunch of definitions, and this one's probably like 6th or 7th. You know, it's not one of the top ones. But let's face it, when we watch a movie, you know, aren't the evil characters always way cooler? You know, Darth Vader, Darth Maul, Palpatine, you know, Star Wars universe. The evil guys are always really cool, right? I mean, come on, Cersei Lannister, who didn't love her? But she was just pure evil. I want to integrate the cube of the secant function. This is definitely one of the evils, but this is an interesting kind of evil. This is a different evil. This is what I refer to, and I affectionately refer to this as the Kaiser-Soze problem. Now, most of you are probably too young to know who Kaiser-Soze is. Does anybody want to offer you may know who Kaiser-Soze is? Zach, who's Kaiser-Soze? Was he a happy, charming guy? Kind of hung out with Santa Claus, or, you know? He's a mythical character. He's a character from a movie, The Usual Suspects. He is supposed to be like literally the most evil person who ever lived, but no one believed he actually existed. And the classic line of the movie, it's one of my all-time favorite movies. I've seen it so many times, and I'm still surprised by the ending every time. You'd think by now I'd know the ending. It's like one of the greatest endings. But he has one of the greatest lines. He says, "The greatest trick the devil ever performed." Do you guys know the answer? If you saw the movie, it's great. He goes, "Making people believe he didn't exist." And the person speaking the line is actually Kaiser-Soze, who's supposed to be literally, you know, evil incarnate. I call it the Kaiser-Soze problem because nobody believes he exists, therefore nobody believes he's evil. And you look at this problem, it looks absolutely friendly and harmless. Oh yes, for a little while. But I'm going to walk you through it because there's a whole series of problems of this nature that we run into in this course. I don't need you to be able to do all of them. I need you to be able to understand what's required to do them. Now, I know the antiderivative of secant squared. I know the antiderivative of secant. So maybe it would be a good idea to break this one up. And what I mean by breaking it up is, what if I rewrote this as, how about secant x times secant squared x? Is that a legal move, first of all? What do you think? Is that a legal move?
Yeah.
Did I change it? Yeah. No, why would I do that? Oh, because then this could be my u, this could be my dv. We cannot integrate secant cubed. We don't know any function whose derivative looks like secant to a power other than secant squared. We know the derivative of the tangent function is secant squared. So this is actually a really wise way to go. Hint, 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 it's the only way to go. So how about if we let u equal secant x, dv equals secant squared x dx, then my du, well, what's the derivative of the secant function? You guys remember? It would be useful. What's the derivative of the secant function? If we were in class, you couldn't all hide. You'd have to volunteer answers all the time, or I throw things at you.
Secant x 10x.
You know, I did give you guys a whole sheet of formulas from Calc 1, and that's a good thing to just have. All right. The antiderivative of secant squared we know is the tan function. All righty. So UV minus the integral of V du. Okay, so minus secant times tangent squared. Beautiful. Now, I don't know anything whose derivative looks like that. Now, there's a couple of things we could do. We could make this secant tangent times tangent, and secant tangent we know is the derivative of the secant, or we could use a trig identity. That might be actually better. Here's the problem with doing this. If I make this tan times secant tan, I can do that. And then that would be my u and that would be my dv. I could do that, but if I do that, I might end up undoing the previous step because you notice we just did that. So maybe that's not a great idea. I think what's a better idea is use the fact we know that 1 plus tan squared x is secant squared x. So that means that tan squared x is secant squared x minus 1. Okay? That actually is a better way to go. I've done this problem before. I'm vouching for that. So I'm going to replace this with secant squared minus 1. Okay? So now I've got secant x tan x minus the integral of, let's go ahead and distribute, secant cubed x, minus secant x. All right. We got one of these kind of things going on. Let me distribute that negative, because we're going to have to pull things apart here. This started off so harmless. All right. I have the secant cubed equals stuff minus the integral of secant cubed. So can I throw this guy on the other side like we did earlier, everyone? Is that a legal move? Pretty much what I have to do. So now, where are we in the process? If I add this to both sides of the equation, I would now have 2 times the integral of secant cubed x dx. And on the right side, I have secant x, I have tan x, and then I have minus the integral of secant. Anybody remember the integral of secant? And again, if you have your integral sheet right in front of you, you can look really smart by knowing the answer, by just looking at the integral sheet. Hopefully some of you are already doing that. That's a plus sign. What's the antiderivative of the secant function? Are we supposed to know that? Actually, yeah. Give you a hint. It's logish. No takers?
That's the log of secant tan x.
Log of, I'm sorry, log of what?
Secant tan x.
Close. Secant plus tan x inside the absolute value. But now we can finish. The integral of secant cubed x dx is equal to half secant x tan x plus half the log of secant x plus tan x. Now, I asked you one really small problem. It's secant to a simple power. And by the way, I directed you which way to go. A lot of us might have just trial and errored this one. No, that didn't work. Let me try this. No, that didn't work. Let me try this. So a lot of people would spend significantly longer on this one because If you didn't do this, you probably would have ended up going around in circles and undoing your work. So this problem, I kind of navigated you, okay? Kind of like Gollum when he gets Frodo and Sam out of the labyrinth of, they never would have found their way out. They just kept going in circles. Yeah, you didn't realize. That started as an integration by parts problem, that whole Lord of the Rings sequence. A lot of people missed that. I have the extended edition. They actually showed the integration, and they just went round in circles on the integration by parts, I think. Anyway, that answer is not really all that friendly. And we only got there by taking all the correct routes as we went. And man, like I said, Kaiser Soze. Okay, this problem is just flat out gnarly. Not my favorite one to do repeatedly, just because it's a lot of work. So, big picture, how do we even know if it's an integration by parts problem? Well, there's really two forms, because I gave you a couple of them. Remember, for example, I only see one function here, but I made it into the product of two. I gave you inverse tan, I gave you natural log. I gave you one function, but we made it the product of two by introducing a one. So an integration by parts problem has to start as a product, the integral of a product. And if you go back to all your Calc 1 integrals, none of your derivatives end up being products of functions. Okay, all of your derivatives end up just being simple functions. Don't confuse that with chain rule. If I differentiate cosine, I get negative sine. If I differentiate cosine to a power, then I have power, cosine, power minus one, chain rule factor. That's different. That's the chain rule. That's not the derivative of the cosine function. That's the derivative of function raised to a power. So those are kind of slightly different rules. So integration by parts, it's a recognition thing. And again, sometimes you have choices. If I've got an E and a sine or an E and a cosine, I have choices of which way to set it up. But if one of my functions is a natural log or an inverse trig, that basically has to be the U. Will you ever end up with a question where you have a product of two things and you don't know the antiderivative of either one? Let me give you something really terrible. I'll combine what we already knew. Let's suppose we had something like that. Can't do it. It's just, not everything has an antiderivative. Not all functions can be integrated, okay? In fact, there are far more functions that cannot be integrated than ones that can. In calculus, we learn all the techniques to integrate things that have antiderivatives that are possible to discover. Then we also learn some backdoor methods of getting answers when we actually can't. Those are some of my favorite problems that we're going to do later. We're going to answer the unanswerable questions. We're going to do an integration of something that has no antiderivative and then evaluate it to answer really important questions. We learn backdoor methods. So I remind people, not everything can be integrated. Now, I'm going to give you a really simple example of that. I know how to integrate the cosine of x. I know how to integrate the cosine squared of x. In fact, we're going to learn, I think next class, how to integrate cosine in general, cosine to the nth power x, where n is a positive integer. We're going to learn how to do that in general. Cool. But what if I said I want you to integrate cosine x to the 1/2? Oh. What if I wanted you to integrate the cosine of x squared? Oh, you can't do those. There's an infinite number of variations of the cosine that have no antiderivatives, and they sometimes show up. We learn how to do the ones that we can do, and then later we're going to learn how to classify the other ones. So in Calc 1, we learned every single antiderivative that if the derivative of one function is equal to one function, then the antiderivative of that one gets me back to this one. We learn about 20 of those, where our antiderivatives are just one function. Now, it might be a complicated function, but it's one thing. In this class, we learn how to do all the techniques that we couldn't do in Calc 1, but we still have to remember our Calc 1 integration. We just integrated in this last problem. We integrated secant squared and got tangent. We integrated secant tangent and got secant. We still have to be, and we also integrated secant and got log secant plus tangent. We still have to know all of our antiderivative formulas from Calc 1. They just happen to sometimes show up multiple times within the same problem. And there is our challenge. So we have to be good, very good at our Calc 1 integration, or it makes it very difficult to proceed because it's hard for me to learn the next thing if I don't know the previous thing. That's why I put online before the semester started that integral worksheet. That integral worksheet I give out in 150, by the way. And I say to those guys, you guys need to be able to do these. Do you have to be perfect on all of them? No, nobody is. But you ought to be able to get most of them. You know, being perfect on most of them is even better because that means you're not going to have a lot of mistakes. But it's really necessary to be able to do the stuff from last semester so we can go forward this semester. All right. Now I've gone as far as I need to today. Let's stop.